In this video cast, we'll work on the vocabulary of chemistry. Make sure that you have your notebook out and a pencil, along with a periodic table handy before you watch this video cast. Naming. Naming in chemistry is described by the word nomenclature, which means the vocabulary of chemistry. Nomenclature comes from the Latin word nomen for name and callare meaning to call. And so nomenclature in chemistry is the vocabulary or the naming of names and formulas. There are two classifications of things that we're going to learn to name. The first one are called inorganic compounds, and that's primarily what you'll be learning over these next 3 semesters. Is a lot of inorganic chemistry. We'll also learn how to name some organic chemicals. Inorganic things are pretty much everything that we're going to learn, which contain lots of metals and nonmetals, and a lot of the things that are around us. Organic things are plants, animals, and living or once living things. The classification is actually expanded to include lots of things, including plastics and polymers, and there are courses that are several years long in college that just deal with organic chemistry, and so we'll definitely touch on that significantly. But we'll focus mostly today on inorganic naming, and in the next video cast a little bit on some of the organic substances. Inorganic things are broken up into 3 particular areas, and today we'll learn about naming inorganic substances called ionic compounds. Ionic compounds are made of ions, cations and anions, positive ions and negative ions, and we'll learn how to put those together and name them. There are also molecular inorganic compounds that we'll learn how to name in the next video cast. And there's a special classification of molecular substances known as acids that we'll learn to name in the next video cast as well. Organic substances that we'll learn are just some simple ones called hydrocarbons, and we'll focus on those in the next video cast as well. So in this one, we're going to learn some of the language of chemistry, particularly of ionic compounds. Ionic compounds contain 2 things. Ionic compounds contain ions. The 2 ions that they contain are a cation, a positively charged ion, and an anion, a negatively charged ion. Keep those 2 straight in your head because we'll use those words a lot. Cation mean positively charged, anion mean negatively charged. Generally, cations come from metals on the periodic table. Almost all the metals on the periodic tables will form positive ions because they lose electrons. And remember, electrons have a -1 charge, and when you lose a negative thing, you actually end up with a +1 charge, or some type of positive charge if you lose 2 or 3 or 4 electrons. Therefore, metals, which are far away from their noble gas counterparts, remember metals are on this side of the periodic table over here, far away from their noble gas counterparts, generally like to lose electrons to obtain a noble gas electron lookalike, or what we'll call electron configuration later on. And remember, they form ions such as +1 in this group, +2 in this group, +3 in this one, and perhaps +4. But we'll find out that those charges are not always true. We'll find out that those are not always true. There are also cations that are groups of nonmetals. Groups of nonmetals that form cations. Now, let's give a couple of examples. Metal examples of cations would be things like sodium, which would be Na with a +1 charge. We write it with a +1 charge because sodium comes from group 1. It's right here, it's element number 11, and it's in group 1, so it will lose 1 electron. Another example would be calcium. Calcium's in group 2, and so it would form a +2 metal. And so we'd write the cation calcium Ca +2, or sometimes you'll see it written like this, Ca++. It means the same thing, a +2 charge. Cations are positively charged ions once again, and these substances in group 1 and in group 2 are always +1 if they're in group 1, +2 in group 2. These are pretty much the only elements on the periodic table that will always for sure know the charge of +1 or +2. Remember, hydrogen always fits over here with the nonmetals, and as a matter of fact, hydrogen can be +1 or -1, as we'll find out later. Okay? Other metals on the periodic table, we might not know the charge of, the positive charge of. And so when we write or we figure out what charge they are, we use a Roman numeral to describe what the charge is. For instance, iron can be +2, or iron can also be +3. And so when we write the word for it, we will write iron, Roman numeral 2, for a +2 charged thing, or iron, Roman numeral 3, for a +3 charged iron cation. All the metals on the periodic table that are in the transition metals, all the metals down here on the bottom in the rare earth elements, and many of the metals over here right next to the staircase, even some of the semi-metals, all need Roman numerals to designate what their charge is. There's 3 exceptions to this rule, and I'll tell them to you right now. Zinc is always +2 and never needs a Roman numeral. Cadmium is always +2 and never needs a Roman numeral. Silver is always +1 and never needs a Roman numeral. Those are the 3 exceptions. Everything else needs a Roman numeral. Oh, I'm sorry, one other exception. Aluminum is always +3. Those 4 are exceptions, and you should memorize what those charges are. Everything else that's in the transition metals, the rare earth elements, or our elements that are along the staircase right near in our metals, can have more than one, can have multiple or different positive charges, and therefore need a Roman numeral like this to describe what their charge are. Just to remember what Roman numerals are, this is Roman numeral 1, this is Roman numeral 2, this is Roman numeral 3, and then remember Roman numeral 4 is an I and a V, Roman numeral 5 is just a V, Roman numeral 6 is a V and I, and then Roman numeral 7 would be a VII. Keep those in mind. There are also groups of nonmetals that form positive charges or cations. Some examples are NH4 +1. This is called ammonium. Another example would be H3O+. This is called hydronium. Notice they end in IUM, hydronium. Also, when I was naming these cations that are metals over here, when I called them an ion, I always called this the sodium ion and the calcium ion, and this would be the iron ion. We usually just call them by their name, and we don't really put a different ending on them. It's just groups of nonmetals right here that we put the ium ending on the end of. And in an ionic compound, when we name or formula write the ionic compound, the cation always goes first. The positive ion is always listed first in the compound. Now, a compound is not only going to consist of a cation, but it's also going to consist of a negatively charged ion called an anion. See, I've listed that right here. Now we're going to go and we're going to talk about a number of these types of anions. Notice cations were usually metals, and they always needed a Roman numeral to tell us what the charge was, except for group 1, 2, and a few of those exceptions. And then, of course, these groups of nonmetals that formed an ion also have a particular charge to them, and you simply have to memorize that charge. Let's talk about anions. Anions are negatively charged ions. They're ones that have gained electrons, because remember, electrons have a -1 charge, and if you gain an electron, you will have a -1 for your charge of the species. Anions can be of 2 classifications. Most nonmetals form anions, and also there are groups of nonmetals that form anions. These two, notice there were groups that formed cations, and now we said that there are groups that form anions. These groups that form cations or anions are called a special name. Since there's more than one atom in them, they are called polyatomic ions. Poly meaning many, atom meaning, atom, what they're made up of. These single cations that are made of one element or one atom of a metal, and these nonmetals that form anions that are one single nonmetal are actually called monatomic ions. They're called monoatomic because mono means one, of course. So poly means 2 or more. Mono means just one thing that has a particular charge. So some examples of anions would be some nonmetals like chlorine, for example, or bromine, for example, or sulfur, for example, or phosphorus, for example. Single elements that form a charge, and if you look at where they are on the periodic table, they're all nonmetals. Chlorine, bromine, sulfur, phosphorus. Nonmetals form negatively charged things, and if you remember, this group will always form -1 charged thing, this group will always form -2 charged things, and this group will always form -3 charged things. We'll find out that in ionic compounds, this holds true 99% of the time. This holds true 99% of the time. So if you, on your periodic table, you don't have -1 written, -2 written here, and -3 written here, do that right now, because this is where you're going to look to find these minus charges for these anions. Now, to name these anions, what we do is we take the name of the element, chloro, and then we add the ending IDE to them if they are a monoatomic ion. So this would be chloride, this one would be called bromide, this one would be called sulfide, this one would be called phosphide. It has the IDE ending to it when it is a single element that's a negative ion. Remember, anions are negative, okay? So nonmetals that form negative ions, which all nonmetals do in ionic compounds, we add the IDE ending to them. And since we know their charge, we don't need a Roman numeral, and anions never have Roman numerals like cations do. So just remember that Roman numerals are always used to form the charge, or to tell us the charge of the cation. Anions never need them because we can always find out what they are. Groups of nonmetals are very, very popular as anions. Groups of nonmetals generally consist of one or more nonmetal and then a oxygen atom. Not always an oxygen, but lots of times. Like, for example, ClO3. This is called chlorate. This is what's called a polyatomic anion. Notice it has a -1 charge. It's made of chlorine and 3 oxygens, and so it's called polyatomic because it contains 3 or more. The only way you know the name of this is by memorizing it. And you will have to memorize a lot of these polyatomic ions. In your textbook, on page number 64, there's a huge list of polyatomic ions, and the problem is that's not all of them that you need to memorize. You'll actually get a handout in class. Actually, in your first packet, you got a handout with lots and lots of polyatomic ions on it. Another example would be SO4-2. This one is called sulfate. SO3-2 would be called sulfide. And if you notice, if it has more oxygen, it has the ending ate. If it has less oxygen, it has the ending ide. So if you saw ClO2, which happens to have a -1 charge as well, what would you predict the name of this chlorine and oxygen containing ion would be? Well, ClO3 is called chlorate. Remember, if it has one less oxygen, it would have the ide ending, and so you would call it chlorite. I'm sorry, I meant sulfite right here. Sulfite has the ITE ending, and this would be chlorite right here. So if it has one less oxygen in the ITE ending, if it has one more oxygen, it has the ATE ending. Another example of that would be NO2 with a -1 charge and NO3 with a -1 charge. NO2 is called nitrite, and NO3 is called nitrate. Ite because it has one less oxygen than the ate. And the only way you know these, once again, is by memorizing the formula, charge, and name of them. And there'll be a number of those for you to name. So when we take the cation and the anion and put them together, the cation and the anion together, we get what's called an ionic compound. A combination of a cation and anion makes an ionic compound. Now, the charges of a cation and anion always sum to 0, always add up to equal 0. For example, let's say we had a cation of Na positive and an anion of Cl minus. Notice the +1 charge of sodium and the -1 charge of chlorine would add up to equal 0, and so the formula of sodium chloride would be NaCl. What happens if they don't add up to 0? Like, for instance, let's say it was calcium together with chloride ion. Well, to write that, we'd need to have 2 of these -1 charged things to balance out the positive charge of calcium. And so to write the formula for calcium chloride, we'd write it as CaCl and put a small 2 down below here, indicating that we need 2 of these -1 things to balance out the positive 2 charge of calcium. This ionic compound would be called calcium chloride. Anyway, always keep in mind that the charges of the cation and anion have to sum or equal up to 0. Here's a number of other examples. Let's take, for example, a compound that's composed of barium, which has a +2 charge. If you look on your periodic table right here, barium is located in group 2. And it's way down here at the bottom. It's element number 56. Can you see barium right there? So barium would have a +2 charge. And let's put it together with a polyatomic ion that is PO4, and it happens to have a -3 charge. Now, there's an easy way to figure out how to sum these charges to 0. Now, you can think in your head, well, +2 plus -3 would not add up to 0, so I'd need to multiply this by something and this by something to get it to add up to 0. And as a matter of fact, you do. If I multiplied this one by 3 and this one by 2, I'd end up with +6 here and -6 here. And these numbers that I say I'm going to multiply by would actually be the subscripts indicating how many of each of these I'd need to make it to add up to 0. Now, there's an easier way to do this. What a lot of people say to do is to take the barium +2 charge and the phosphate -3 charge and to drop and swap their charges. Drop and swap their charges. Now, this formula easily becomes BA with a small 3 down below it. Get rid of the little negative sign and the little positive sign here. You don't need that. And then I'd write PO4, and I'd have to indicate that there are 2 of those because I dropped the 2 and swapped it. And so to do that, I'd put this in parentheses and put a 2 on the outside. You could put parentheses around anything you want, but notice that the 2 speaks to everything inside of the parentheses right here, indicating there are 2 of this -3 thing. And there are 3 of this barium right here. Could I put parentheses around the barium? Sure. Is it necessary? No, because there's only 1 of them. But anytime you have a polyatomic ion, remember an ion that has more than 1 atom, then always put parentheses around it if there's more than 1. Well, let's go on with some examples of naming. Let's pretend that I have the formula CaCl2. What would be its name? Now, we did this one as an example earlier, but the first thing you do is name the cation, calcium. And the second thing you do is name the anion. Now remember, the anion, since it's negative, if it's monatomic, there's only 1 kind of them, you just put the ending IDE on it. So we'd call it calcium chloride. Now remember, we said the metals generally need Roman numerals to indicate what their charge was. Remember, all the metals on the periodic table need that, except for ones that are in group 1 and in group 2, and these couple of exceptions that I wrote over here. Well, it so happens that calcium is right here in group 2, and it has a +2 charge. And if you look over here, chlorine is in this group, and it happens to have a -1 charge. Therefore, that's why in the formula we have 2 -1 charged chlorines, and we have a +2 charged calcium. Since we know calcium's charge is always +2 because it's in group 2, we don't need to put the Roman numeral 2 there. You could put it in there if you wanted to, but it's not necessary. And generally, the Roman numeral is put in parentheses like that. Not always, but generally. Let's look at a second one. CuClO4, 2. First, name the cation. Cu is the element copper. If you haven't memorized the names of your elements yet, please do. And then ClO4, you need to look up on your list of polyatomic ions, because it's a group of nonmetals put together that has a charge. As a matter of fact, when you look up ClO4 in your book or on your sheet of polyatomic ions, you'll find out ClO4 is called perchlorate. Perchlorate. Now, take a look and make sure that your cation right here is one that needs or does not need a Roman numeral. Remember I said all of them need Roman numerals except for group 1 and group 2. Is copper located in group 1 or group 2? No. Copper is located actually way over here, and copper is not one of those special elements that I wrote the charge of and said you should memorize. So copper needs a Roman numeral. How do we figure out what the Roman numeral for copper is? Well, we take into account that we know the cation, this thing, and the anion, this thing right here, have to add up to equal 0. They have to sum to 0. That's the mathematical term for it. So whatever copper's charge is, and therefore its Roman numeral right here, I'll put a blank here because we don't know what its charge is, plus whatever chlorate's charge is, have to add up to equal 0. And we know that there are 2 of these chlorates because there's a 2 outside the parentheses of this thing. I circled it to get aware, and now you can't see those parentheses quite as well. So I'm going to need to multiply whatever chlorate's charge is by 2 and then add that to copper's charge to find out what it is. Now, you can look up what chlorate's charge is because you're either going to memorize it, or you're going to be able to look it up in your textbook. And if I just show you my textbook here really quick, you can see that perchlorate is right in the middle, ClO4, and what is its charge? ClO4 has 1 minus sign next to it. So perchlorate ion is a -1 charge. So what I have is now a little mathematical equation. Some number plus -2 is equal to 0. What must this number be? Well, it's obviously got to be 2, which is my Roman numeral. Therefore, I'd put a Roman numeral 2 in the middle here, indicating that copper is a +2 charge. Because remember, whatever this charge is, plus this total charge here, has to sum to 0. So whenever you don't know what the Roman numeral is, you have to write a little mathematical equation like this to figure out what the charge could be. Second of all, third of all, let's take a look at this one. Fe is called the element iron. Cl, of course, is the element chlorine, but since it's an anion, remember we add IDE to it, so we'll call it chloride, IDE. And then we have to look on our periodic table to see if iron's one of those that needs a Roman numeral. Remember, if it's in group 1 or 2, it does not need a Roman numeral, but it turns out that iron is way over here, and it's not one of those that has a special charge that we already know. So iron can be several different charges, and we need to indicate with a Roman numeral what that charge of the iron ion would be. How do you figure it out? Well, you write a little mathematical equation, and you say whatever iron's charge is plus whatever chlorine's charge is times 3 is equal to 0. Remember, it always has to sum to 0. We're lucky because chlorine on the periodic table is from group 17. And in group 17, everything, including chlorine right here, has a -1 charge. So since we know chlorine's charge, we could figure out what iron's is. Chlorine is a -1 charge. So some number plus -3 is equal to 0. Therefore, iron must be 3. So we write the Roman numeral 3 in there, and it would be called iron 3 chloride. See why it's important to put the Roman numeral 3 in there? Because it could end up being 2, or it could end up being 6, or it could end up being something else, and you need to tell the world what is the charge of this iron ion. Last one, NH4,3PO4. This one looks difficult. As a matter of fact, it is until you become familiar with your polyatomic ions, your ions that have more than 1 atom in it. Well, if you look up NH4 on your list of polyatomic ions, which if you look on page 62 in your textbook, it'll show you, or on your list of polyatomic ions, you'll find NH4 listed right up here at the top. NH4 positive 1 is called ammonium ion. See, NH4 plus? Ammonium ion. So I would just write down ammonium, and then I would look up PO4, which is another polyatomic ion. And this one happens to be negative, so we'd call it an anion. And if you look on the list of polyatomic ions, there's PO4, and it happens to be a -3 charge, and it's called phosphate. And so I write down ammonium, and then I write down the negative ion, which is called phosphate. And ammonium phosphate is the name of NH4,3PO4. PO4. Notice I needed 3 of this positive 1 thing to balance out the negative 3 of the phosphate. Now I didn't need to figure that out at all because it's not going to have a Roman numeral. As a matter of fact, polyatomic cations never have Roman numerals. But I just wanted to show you that they do sum to 0, which is one of the things that we wanted to make sure of. Let's go backwards. Let's go backwards. And let's say, for example, that we wanted to write the formula given a name. Let's say, for example, we had the name strontium hydroxide, and we were told to write the formula. Well, the first thing we want to do is we want to write the cation strontium, which is Sr. And you want to look on your periodic table and find out what its charge is. Since it's an ionic compound, the ionic compound will always have a cation with a positive charge and an anion with a negative charge. Strontium is located right here on the periodic table, which is in group 2, so it has a positive 2 charge. So strontium is +2, put the little +2 up here on the top, and then hydroxide we need to look up. And if you look on your list of polyatomic ions, hydroxide is OH, and it has a -1 charge. Now when you put these two together, remember the charges have to sum to 0. And one way that I showed you that's easy to do this is to drop and swap the charges. Drop and swap the charges. And you end up with the formula Sr, OH, and I have to indicate that there are 2 of these OHs. So if I just put a 2 right here, I'm in trouble because I've only indicated that there are 2 H's. I want to indicate that there are 2 of the entire hydroxide polyatomic ion. So I need to put this into parentheses showing that the 2 speaks to everything inside of those parentheses. This is called strontium hydroxide. Okay? Next, cobalt 2 nitrate. Cobalt 2 nitrate. Cobalt's symbol is CO, and it has a Roman numeral of 2. Remember, the Roman numeral tells you the cation's charge, and the cation is always listed first. And so cobalt has a positive 2 charge. Where did I get this +2 charge? Because it has a Roman numeral 2 right here. If I look at cobalt on the periodic table, it's located way over here in the middle, and it does not have a charge that I know. That's why it has a Roman numeral, because that tells us the charge. Next, I need to write down the formula for nitrate. Nitrate, if I look it up on the periodic, not on the periodic, on my list of polyatomic ions, is NO3 and has a -1 charge. Notice it's a mixture of 2 or more atoms that have a charge. Next, drop and swap the charges. Drop and swap the charges. Get rid of the plus and the minus right there. And then I need to write it as CO NO3 and put a small little 2 down here because there were 2 cobalts, so I'd need, a positive 2 charge for cobalt, so I'd need 2 of these negative NO3 ions. Tin 4 phosphide. The element tin is Sn, and notice it has a Roman numeral IV or 4, which means it's going to have a positive 4 charge, and phosphide ends in IDE. Now a lot of people get confused by this because this is kind of tricky. Remember, if it ends in IDE, that means it is a monatomic nonmetal. Mono meaning 1 atom ion, so it would be P -3. How do I know that it's -3 if I don't have my notes in front of me? Well, I can look on my periodic table, find phosphorus, there it is. Happens to be in group 15, which are all -3s when they're in ionic compounds. P -3. Okay, drop and swap the charges. The 4 goes over here, the 3 goes over here. Remember, get rid of the pluses and minuses. It's now SN3, P4. That's tin 4 phosphide. Tricky ones, let's look at a couple of them that are kind of strange and ones that'll try to goof you up. PbO2. Now we're going from formulas to names once again. And some people will say, well, I can figure out this Roman numeral thing really quick because you told me how to drop and swap up above right here, and really the Roman numeral, if I look at it, is just this number undropped and swapped, right? Because it'd be tin 4, right? Or in this case, cobalt 2. Oh yeah, it's just this 2 right here, and I dropped and swapped it, so that means cobalt is +2. So if I undrop and swap this one, it would be lead 2. be careful of doing that. That's why this one is in the tricky ones, and there are a few others like this too. PB is called lead, so name it lead. Okay, O is called oxygen, so make sure to put the IDE ending on it, because remember, if it's a monatomic single element monatomic ion, it always ends in IDE, and oxygen by itself is a monatomic ion, so it ends in IDE. So it would be called lead oxide, always ended in IDE when it's a single element. And then we need to figure out what the Roman numeral is, because lead is located over here on the periodic table, and we're not exactly sure what its charge is. Remember, all metals, we don't know what their charges are except for these special 4 right here and the 2 groups over here on this side right here. So lead's charge we need to figure out. And like I said before, you can't just undrop and swap. Here's why. Oxygen, we can look on the periodic table and we can find out that that's in group 16. Group 16 has a -2 charge. Group 16 oxygen has a -2 charge. Always. Okay? So oxide is -2. There happen to be 2 of them right here. Uh-oh, so I have to multiply this by 2. I know it has to add up to equal 0, and what must lead's charge be? Something plus -4 is equal to 0. Lead's got to be +4, so I have to write IV in there. Now, if you just undropped and swapped it, you would have put lead 2 oxide and you would have been incorrect. That's why this is a tricky one. So be careful. Always write your equation like this to figure out what the charge of the cation is. Don't just undrop and swap them. It works sometimes, but not all the time. Writing the equation always works. Here's one that's not too tricky. It just looks kind of strange. W2O7. Well, W is the element tungsten. And O, once again, is oxide, IDE ending because it's a monatomic ion. And then tungsten, of course, we need to figure out what the charge is. Well, this is a little bit more complex mathematical problem. Oxygen, remember, is in group 16 right here. So it has a -2 charge when with the metal. So we've got -2 times 7 now, because there are 7 of them, equals 0, plus whatever tungsten's charge is times 2, because notice there's 2 of them. So some number times 2 plus -14 is equal to 0. That means tungsten must be 7. Oh my gosh, yes, tungsten 7 oxide, as a matter of fact, the name. Tungsten 7 oxide. That one's kind of tricky. All right, these last 2 are the trickiest ones that you'll encounter. They involve the element mercury. Mercury has 2 forms. There's mercury 1 and there's mercury 2. Mercury 1 is a strange polyatomic cation. Mercury 1 is 2 mercury atoms stuck together, each with a +1 charge. And since both of them have a +1 charge, the overall charge of this cation is +2. Each one has a +1 charge, but they always exist in a pair like this. And so some people call this a diatomic cation. That's mercury 1, because each one has a positive charge. Mercury 2, though, is Hg, and it simply has a +2 charge. It's only 1 atom. And this is what makes mercury confusing, is you have to remember that mercury 1 is actually diatomic, 1 with each a +1 charge, for an overall charge of 2 of the diatomic cation, whereas mercury 2 is simply Hg plus 2. Now they're both combined with chloride, and if you remember, chlorine is a -1 charge. Chlorine has a -1 charge because it's in group 17 on the periodic table. Now drop and swap them. Drop and swap them. And when you do this, you end up with, for mercury 1 chloride, Hg2, because there's a small 2 down here, Cl2, and over here you end up simply dropping and swapping, and you end up with HgCl2. So notice the difference between these two now. This one has 2 mercury atoms in it, each of +1 charge, adding up to a +2, which is dropped and swapped down here. This one has 1 mercury atom in it with a +2 charge, and it's dropped and swapped down there. That is the confusion of mercury 1 and mercury 2. Good luck with your naming of ionic compounds.